Hello everyone, thanks for joining the SONiC session. Today we're going to talk about the SONiC troubleshooting experiences at LinkedIn. My name is Jinggen Xu. I'm a software engineer, and this experience is it's pretty much like a deep dive to the SONiC components, to really get to the bottom of some of the issues. So before we get into the details of those experiences, just a few words for LinkedIn. I think we have close to 700 million members today, and we have 5 data centers globally, and 250k servers, and many thousands of switches. The SONiC is the default network OS for the switches in data center. So this slide is just to show you like the SONiC architecture, right? This is not I'm not going to go to the very detail. It's just to give a high level overview of the SONiC architecture. Like SONiC is basically sitting on top of Linux, it has some hardware, then kernel drivers and basically based on the kernel, right? Debian kernel. And this is also very database centric. And as you can look at it, it's Redis basically a server. It's in the middle of the system. And there are many Dockers here. They're working together, to make sure the protocols, the different applications can be managed through all these Dockers and set to the kernel and the hardware. Right. So these Dockers, they're coming from different open source places, as well as like they developed in SONiC itself. And as you know, like they have different languages like C++ or C or Python, different language developed for different components. So this is will highly impact what technique we use, what tools we use, when we debug those things. So okay, first let's talk about like Linux troubleshooting, because the SONiC is sitting on top of Linux. So we would like to really leverage a lot of Linux tools, to get some debugging straightforward, right? So the Linux is there's a lot of tools for the networking stack, right? Like IB tools or and neighbors, show tables, and traffic, pinpoint tools. And also, if you have some syscalls, you're stuck somewhere, you can use this so syscall calls to really debug the daemons. And also you have some stats, the control plane stats basically, right? As well as like IP tables and some monitoring for the IP. Right? So one of the example we did for the Linux kernel troubleshooting was, we hit this very interesting problem. This is problem we solved like a few months ago. This is basically we have like a DNS servers, right? And this is not working basically on over IPv6 on this new kernel. Basically, it's 4.9. The reason we say this is interesting is like this is really, initially it's really was really struggling to understand what's going on. For example, it's working on IPv4, and also if you use a TCP option for the DNS query, actually even on IPv6 is working, right? And also with the old kernel, it worked fine. And we did some TCP dump, the request sent to the DNS server, when it come back, the packet looked normal, even the checksum, everything looks fine, right? So we did quite some debug here, like for example, trying to disable the UDP offload, for example, that didn't help. And the one thing I think it came up to our mind is that probably like some IP tables actually played a big role here. We have actually the SNAT enabled for those DNS packets because of the topology usage. And we disable the SNAT, then it worked right in the lab. So we know, okay, there's something to do with the SNAT. And also we checked here some system stats, and we see some checksum error. So eventually we hooked up the like kernel modules and find, okay, it's really a kernel bug, right? This bug is really, in a corner case actually, when you have SNAT enabled, the UDP checksum is not actually calculated correctly after the translation. And for IP4 actually worked because IP4 has IP layer checksum. I think that somehow that function worked okay. And TCP checksum is completely different, so that's why it's also working. If you have interest, I think look at these two links. It has the details of this the fix. The fix is actually not big, but is really a kernel module. The key components there. Okay, as I said, like a SONiC, depending on database, a lot. So we want to give you some examples how to troubleshoot a database. So we heavily rely on the Redis CLI, when we debug things, right? Basically, you can check different tables. You can monitoring the database in and out, and we can check the memory consumption. We can check, the client's information and some metrics. One of the example we had was one of the problem we had was the link flap. Continuous link flap can cause out of memory issue. This is when the link flaps, actually BGP may add or withdraw the routes continuously, right? And these routes were pushed to the database, through FPM syncd to the AODP, and then got taken by the OC agent, then pushed to the hardware, right? That's the overall flow. But the observation we had was that this actually, the Redis DB take a lot of memory over time, and the OC agent is not fast enough, basically, to process those requests. And if it keep continuous flapping, the Redis will consume all the memory and will basically crash the system, right? I mean, we could put some, memory constraints for different daemons, but that is not. That's just a mitigation plan. But here it's trying to really it would cause the problem. So we did a few things also, trying to understand. We will provide the OC agent, but there's no big difference, before or after the link flap cases. And when we and then we started to check the Redis itself. We use the CLI monitoring, we use the memory commands, we use the client's commands to really say where the problem is. For example, you can see what keys came to the Redis. You can see what clients actually have biggest outputs. You can see how much memory is used and so on. So eventually, the root cause is pretty it lies on the mechanism we use between these different Dockers, right? How do we pass things around, right? So before the fix, basically the thing is when we push the key to the AODP, at the same time we send a notification, right, to the consumer. And as you know, like a number of routes actually in data center, at least in our data center, is kind of, we know the boundary, right? Let's say you have 10K routes, and this memory consumption for 10K routes, in memory in Redis is fixed. It has a maximum because it's using hash table. So you know exactly like how much memory to consume. It's actually quite small, right? However, there's a notification channel, right? If you write one key, you have one notification, and if this consumer is slow, this notification channel will be built up over time, and it basically will consume more and more memory. So that's really the key problem here, right? So the fix we had was okay, if you have the key, if the same key, right? If you write something to the AODP, and if the same key is already exists, you don't publish notification. So that was one fix. That's actually worked pretty well if you have like a fetched key one at a time. However, we did a lot of optimization in this producer consumer tables, where we have batch mode. So during a batch, actually one notification you can fetch like a lot of keys, right? So in that case, actually this notification can still be built up even if you continue wrapping. So eventually we just publish notification per hash set, right? So that you can make sure there's no like really accumulated increasing of the memory. Okay, so next one is like the SONiC core daemons, SWSS Docker and the Simply Docker, right? And so as we mentioned before, it's basically pretty much using C++ for all those daemons, and to really deep dive to those, the troubleshooting those problems, we use GDB basically, right? In our case, actually, we put symbols. We build all the daemons with symbols and on the production image. And of course, like during if you have some crash, you could check the core files. They give you an idea, where it's crashed and how the core stack look like. And we use Redis CLIs to also to check different tables. We can use benchmark tools to really get understanding the CPU utilization or usage, by different daemons and functions. And the SI, the one important thing here is the SI. They have a lot of tools and records on the system. The SI dump will actually give you an instant view of the ACDB basically, right? And the SI records and we will keep the SI records by default right on the disk. So any transaction between the SWSS and the ACDB, you have a transaction there, right? And these things can actually be played later or use SI player. So this is very good for ASIC vendors, to reproduce the issues. And yeah, we use Windows CLIs to debug something, and the syslog, of course, is always good to if you have errors, you have something for different daemons, you can turn on different log levels actually to see it. So this is just a very this just give you a very simple example to show how we can use GDB to debug some of the issues. For example, this is like some Stack Overflow issue. We fixed this a long time ago, but it's just showing an example. And as you can see, it has 20,000, core stacks here. It's and of course it will crash because it's running out of memory, right? And yeah, it can give you exactly 9 numbers, and exactly if you look at the code, then you know what's going on, right? And the second issue was about the key orders. I think we developed some features actually we didn't know, like the key order was issue for the SI, but so we didn't pay too much attention at the beginning. But basically, when you write the key, write multiple keys to the config DB, right? And when consumed by some management daemon and push to AODP, and then to the occasion to SIDB, the order are not kept to the end, right? As you can see, like some steps here, like when actually the keys were popped, to org agent, they're already out of order. When you process the org agent, it's also out of order, right? So eventually the fix was that we because these keys actually they're independent objects in config.db, and they don't really necessarily have any dependencies in terms of configuration. So in this case, we ask the side vendors to fix that. And but if you have so much keys, they have to be dependent on each other. And in this case, I think the org agent should handle those dependencies, right? You should have some retry logic. You should wait for those dependencies to come and before you push to the site database, right? And also, if you really need some orders, like strict orders, even there's no strict dependency, you might be use a different mechanism. For example, the config.db mechanism, which is keep the order. Yeah. Next one is the there's some syncd troubleshooting, and I think this is also very it's old problems we solved. So we noticed that when we install the routes to the hardware, and the time increase was not linear in terms of like number of routes. So it's actually increased like exponentially, which is made us wonder what's going on, right? So we use Docker actually commands to find out like the process flows, like what process they consume more and how the timelines, coordinated, and then we use some performance benchmark tools actually to profiling the syncd eventually, right? And we can see, there's some very suspicious functions actually consume a lot of CPU power whenever this lot of routes in place. So we fixed some data structures in the in the code, and then yeah, those suspicious issues are gone, and we can see the installation time is linear now. Okay, so next one is the SMP related. As you know, like SMP is reading in C, so and there's also subagent. It's done by SONiC community. It's in Python, to prepare those MIPS and so on. And we use PDB to debug those things. And SMPD itself, we use GDB, and of course you can use the SMP worker bucket, to do some stress test. And you have some profiling tools actually can really get understanding the again, the profiling during the stress test. So one of the problem we had was CPU spikes and SMP separation timeouts. This problem is we saw this problem, but we really don't know what's going on. It's if you really look at it, it's just some messages. You don't know how to debug, where to find out. We attached the GDB to SMPD, and we see some timeouts, but so what? We don't know what's going on really. And we use some Python extension and with GDB, and we can actually attach to agent. But still, it gave you some trace, code trace, but it didn't give you why it consumed that much this CPU, right? So we we also did some like workarounds, change timeouts, those things. I mean, those are not really a solution, right? We didn't really understand. So we noticed that based on the Linux commands, we know like the Redis server actually consume all the most of the CPU cycles. So we're trying to use the PY flame attached to the subagent, and then we saw that the one function actually take a lot of time, right? This function is It's basically basically this is in this case actually we have a lot of Macs learned from the application on this box, right? And when you do the MIPS, it's actually when we send those MIPS for the Mac, it's actually do a lot of transaction with the Redis, and of course that will consume a lot of cycles on the Redis server. And the fix is very simple. We just keep a local cache, and then the CPU reduced like it's significant. It's like 80% to like 1%, something like that, right? So again, the fix is it's simple, but to find the problem is very tough. So we have to use all these Linux tools. Next one is the AODP issue. It's it's in C, and we use GDP to debug things, especially like in some cases we know, like in this case actually we see like a bad behavior, like AODP sometimes doesn't advertise some interfaces, and it's just inconsistent. We don't know what's going on, and we attach GDP, and we use like GDP some scripts, you dump the internal data structures and so on. We really need to understand, all those structures. Then we realize, okay, this could happen, if the netlink is missed. Some netlink is missed for the interfaces. And so the fix is simple. It's just to increase the buffer size. The reason was because we have so many interfaces. The default buffer size is not big enough. The CLI, this is not the session for how to debug CLI yourself, but it's more like how we use CLI to debug other things. We use a lot of Linux tools like pipe filters and watch commands to see periodically monitoring stuff. And we use Windows CLIs to check hardware and debug really the hardware things. And if the CLI itself has some problem, some crash or something, we use PDB, or we just typically it's very easy. Actually, it's Python. You can debug on the box itself, modify things on the in the box itself. So some examples. I think it's it's not for the Linux guys. It should be pretty straightforward things. You can use watch command to periodically show things, and you can use grep to find whatever you're interested. And the other things like show interface stats, we can show like the link flaps, for example, and the timestamps. Those things is pretty useful. Okay, the next one is system level troubleshooting, and this data center. There's a lot of boxes in the field. They're connected to each other. And sometimes it's the problem is not because of one box is malfunctioning, but it's more like system level, whether it's configuration or some other issues, right? So to have this troubleshooting, we usually use the telemetry data. Basically, we have time series database, to save all the events and the traffic, and other information, right? So for those things, you can actually see what is the trend and what happened in what time, because it's time series. You can look back at the history. And on the box, of course, you can show the user CLI to show different things. Show the errors, drops, or rate limit drops. Like congestions, or even if you monitor it close enough, you can see some of things probably microburst. And of course, the syslog, it's very good to show the events and some details. Audit log can help you to understand what operations have been done before this issue happened. And we also do like route consistent check. We build some tools here internally to check those consistencies from different levels, right? And one of the issue we hit was the traffic distribution, right? They are not distributed equally to the to the what we call the fabric. It's the spine layer, to the spine layer basically. I mean, this is also interesting. As you know, like we use BGP, use ECMP, in the data center, mostly in many data centers, and the distribution, is pretty much rely on the hardware and hash, right? And then you may be wondering why that hash is not working, right? So that's the thing. And we actually did a few troubleshooting things. We disabled some links. Actually, it started to distribute well, right? And then we realized, I think the Tor uplinks and the leaf uplinks, they are like is multiple or factor of the other one, right? So as you know, like the hash is based on basically 5 top typically, and this flow is never changed. The 5 top never change in these flows. So if somehow those uplinks, they're a factor or multiple of the other one, you may hit the same same number, same hash value basically at the end. So eventually, this is the problem: is the hash polarization issue, right? Where you have the same hash seeds and then they will hash exactly the same value. So that's the problem, right? So of course, this is the configuration issue. Actually, we changed the seeds, the hash seeds, and eventually it worked fine. Okay, so the takeaways for this presentation, I think I want to highlight this: really we want to leverage the Linux experience and tools to do the troubleshooting. Like a lot of networking stack commands and profiling tools and the CLIs, those things, filters and so on. It's very very neat, for any troubleshooting. And we also leverage Docker for isolation and the stats when you debug something. And the Redis DB we use monitoring and also trying to verify by CLIs. And have GDB or syslog for those deep issues in the daemons. And the other things like this SWSS and site records are very good in terms of you're gonna want to reproduce the issues offline. And the telemetry data is very good to get the trends, so to get the events, the tiny matter, and also you can look back to history, and also rely on the consistent checks from application to hardware. So yeah, that's it for the talk. The call to action is really, please contribute to SONiC. I think it has pretty a big community, but we still would love to get more contribution. Even if you just see some bugs, see some issues, just report there. It could help, to improve the quality of SONiC. Yeah, that's it. Thank you.